Hello, everyone, and welcome to today's session on Python interview questions and answers for freshers. I'm excited to have you here. Today, we'll be focusing on part 2, which covers Python syntax and semantics. In this presentation, we'll explore some essential concepts that will help you prepare for Python interviews. We'll go through key questions and their answers, making sure you get a clear understanding of how Python works under the hood. So, let's get started and make this a productive session. Let's take a closer look at Python's built-in data types, which are fundamental to writing effective code. Python offers a versatile type system that helps us tackle a wide range of programming challenges. Understanding these types is key to using the language efficiently and correctly. Starting with numeric types, we have int for whole numbers of any size, thanks to Python's unlimited precision. Float is used for double precision decimal numbers, which are great for most calculations involving fractions. Complex numbers, which include real and imaginary parts, are also available for more advanced mathematical operations. Interestingly, bool, which represents true or false, is actually a subtype of int, so true is essentially 1 and false is 0. Moving on to text data, the str type allows us to work with strings of Unicode characters. This means Python can handle international text and emojis seamlessly, supporting full Unicode, which is incredibly helpful for global applications. When it comes to sequences, Python provides list, which is mutable and very flexible, tuple, which is immutable and great for fixed collections, and range, which is used for creating immutable sequences of integers, especially useful in loops. For mappings, we have dict, which stores key-value pairs. This makes data lookup and organization very efficient, an essential feature for many applications. Set types include set, which is mutable, and frozen set, which is immutable. Both store unordered collections of unique elements. This is useful for operations like membership testing and eliminating duplicates. There are also other types like bytes and byte array for binary data, which are essential when working with raw data or files. And of course, none type, which has the single value none, representing the absence of a value. A quick tip, you can check any object's type using the built-in type function. For example, type 123 will tell you that it's an int. By understanding these data types, we can write more precise, efficient, and readable Python code, connecting these concepts to the larger goal of mastering the language for any project. Now let's explore the difference between mutable and immutable objects. Mutable objects are those that we can change in place after we've created them, without needing to make a new object in memory. For example, with lists, if we start with mylist equal to 1, 2, 3, and then we do mylist, append 4, the list updates to 1, 2, 3, 4 directly. Similarly, dictionaries allow us to add, remove, or change key-value pairs, and sets let us add or remove elements dynamically. Byte arrays are another example. They let us modify binary data directly. On the other hand, immutable objects cannot be changed once they are created. If we try to modify them, Python will create a new object instead of changing the existing one. For example, numeric types like integers, floats, and booleans are fixed. Once you create a number, it doesn't change. Strings are also immutable. If you have s equal to hello and try to change s0 to h, Python will raise a type error because strings can't be altered directly. Tuples are immutable sequences, meaning their contents can't be modified after creation. The same goes for frozen sets, which are immutable set collections. The key insight here is that when you attempt to change an immutable object, Python doesn't alter the original. Instead, it creates a new object in memory. This behavior is important to understand because it impacts how your code manages memory and performance, especially when working with large data structures or in situations where mutability matters. Connecting this to the overall theme, recognizing whether an object is mutable or immutable helps you write more efficient, predictable code. Let's talk about integers and floating point numbers in Python. Python's numeric types are quite flexible and precise, which makes them really powerful for a wide range of mathematical operations. Whether you're doing simple addition or complex scientific calculations, these types have you covered. First, let's look at integers. Python's integers are what we call arbitrary precision, meaning they can grow as large as your memory allows. There's no worry about overflow here. For example, you can store a huge number like 12 quintillion 345 quadrillion 678 trillion 901 billion 234,567,890 without any issues. This is a big advantage when dealing with large data or precise calculations. Moving on to floating point numbers, these follow the IEEE 754 standard. They provide about 53 bits of precision, which is enough for most scientific purposes. They're great when you need to work with decimal values, but keep in mind that they have some limitations in precision compared to integers. Now, sometimes you need to convert between these types. Python makes this easy with constructor functions. For instance, int 3, 7 will give you 3 because it truncates towards 0. Similarly, float 4 becomes 4. You can also create complex numbers with complex 2, 3, which is useful in many mathematical applications. Lastly, a fun fact. The bool type in Python is actually a subclass of int. That means true is equivalent to 1, and false is 0. This connection allows booleans to be used seamlessly in numeric calculations, which is quite handy in programming. So, understanding these numeric types and conversions really helps us write more efficient and accurate Python code, especially as we handle more complex computations. Let's talk about division operators in Python 3. Python 3 made some important changes here to make division more intuitive and predictable. First, there's the slash operator. This performs what we call true division, meaning it always gives us a floating point result, no matter what types of numbers we're dividing. So, for example, 5 divided by 2 using will give us 2.5. Similarly, 4 divided by 2 results in 2, and 2 divided by 2 gives us 1. Next, there's the double slash operator. This is known as floor division. It divides and then rounds down to the nearest whole number, which is especially useful when we need an integer result. For instance, 5 2 equals 2 because 2.5 rounds down to 2. And if we try dividing 2, it results in minus 2 because it rounds down towards negative infinity, not just truncating. Then we have the divmod function, which is quite handy. It performs a combined operation. It gives us both the quotient and the remainder at once as a tuple. For example, divmod 17 5 returns 3 2 because 17 divided by 5 is 3 with a remainder of 2. It's also important to remember that in Python 2, the slash operator would perform integer division if both operands were integers. But in Python 3, this behavior changed to ensure more consistency. Now, the slash operator always produces a float, which aligns better with our expectations and makes our code more predictable. Let's dive into understanding strings. Core characteristics first. Strings, or STR, are immutable sequences of Unicode code points. That means once a string is created, it can't be changed. This feature allows strings to support international text and symbols seamlessly. When it comes to creating strings, there are several methods. You can use single quotes like hello or double quotes such as world. For multi-line strings, triple quotes are handy, for example, multiline. Now onto common operations. Strings support many built-in methods and operations that make handling text easier. Concatenation is straightforward. Just use the plus sign like hello plus world to combine strings. Repetition works with the asterisk. For example, ha asterisk 3 results in ha ha ha. Slicing allows you to extract substrings, say S1. 5 retrieves characters from position 1 up to 4. There are also useful methods like supper, to convert text to uppercase, split, to divide a string into parts, and strip, to remove whitespace from the beginning and end. These methods make string manipulation flexible and efficient. Since strings are immutable and hashable, they can serve as keys in dictionaries or elements of sets, which is a powerful feature in Python. But it's important to remember, any operation that seems to modify a string actually creates a new string object. So, strings are essentially unchangeable once created, which helps keep data consistent. Connecting this to our overall theme, understanding these core properties of strings helps us write more reliable and predictable code, especially when dealing with complex text data. Let's talk about none and Boolean values in Python. First, none represents the absence of a value. It's a special constant, uniquely serving as a placeholder for nothing or null. There's only one instance of none, called none_type, which makes it a singleton object. Now, why do we use none? It's commonly used as the default return value for functions that don't explicitly return anything, or as a placeholder for optional parameters. Plus, it's handy when initializing variables before assigning them actual values. A best practice when checking if a variable is none is to use the is keyword like this, if my var is none. This ensures we're testing for the specific none value, not just a falsy value. Moving on to Booleans, Python's bool type only has two values, true and false. These are used extensively for comparisons and logical operations. For example, if you compare 5, 3, the result is true. Logical operators such as and, or, and not help us combine or negate conditions. In a numeric context, true behaves like 1 and false behaves like 0. This means they can be used in calculations or with bitwise operators like and, which also work with Booleans. Finally, it's important to understand that none is different from false, 0, or empty strings. Each of these has a distinct meaning in Python, so mixing them up can lead to bugs or unexpected behavior. Recognizing these differences helps us write clearer, more reliable code. Let's talk about type checking and conversion in Python, which are fundamental skills for writing robust programs. First, checking types. Python provides the type function, which helps us determine an object's type at runtime. For example, type 123 returns class int, type hello returns class str, and type 123 returns class list. This is especially useful when debugging or validating input data to ensure it's what we expect. Now, moving on to converting types. Python offers constructor functions like str, int, float, and bool to explicitly convert between types. For instance, str123 gives us the string 123. Similarly, int 456 converts the string 456 to the integer 456, and float 314 turns the string into the floating point number 3.14. Converting a float to an int, like int 3.9, truncates the decimal part rather than rounding, so it results in 3. It's also important to note that string-to-number conversions require the string to be a valid numeric literal. Otherwise, Python raises an error. Speaking of errors, one common gotcha is trying to convert a non-numeric string with int or float, which leads to a value error. For example, int ABC isn't valid because ABC isn't a number. Another important point is about truncation. Int 3.9 results in 3, not 4, because Python simply cuts off the decimal part. And finally, when it comes to truthiness, empty values like an empty string, 0, or an empty list all evaluate to false in Boolean contexts. These are what we call falsy values, which is a useful concept when writing conditional statements. So, understanding how to check and convert types effectively allows us to handle data more safely and predictably in our programs, which aligns perfectly with our goal of writing reliable and maintainable code.